Happy last week, seniors. Happy second to last week, everybody else. We're finishing 12.1 today, just looking at properties of limits and how we can do direct substitution. We had an example last week that said the limit of f of x as x approaches c was just plugging in the value of c and getting that y value. So if that's the case, then you can just do direct substitution. So like we said, the limit of f of x as x approaches c is just f of c. So there's a lot of functions that we can just use direct substitution. So these four properties are true about these basic limits. So number one, if we're taking the limit of just some number, so that's going to be a horizontal line, the limit as x approaches c value is just going to be the same y value of that horizontal line. So graphically, if here's my graph, this is my function. So whatever my target is, as I get closer and closer to that x value, my y values are always going to get close to the same target. Number two says the limit of x as x approaches c is just c. So this function is just a linear function with a slope of 1 and a y-intercept of 0. So as we get close to whatever our target value is on the x-axis, that y value, or the limit, is going to be the same number on the y-axis. So this graph just goes up 1 over 1, up 1 over 1. So whatever the x value is, the y value also is. Number three, the limit of x to the n as x approaches c is just c to the n. So again, we just substitute that c value in for x and find that y value. And then number four, the limit of the nth root of x as x approaches c is the nth root of c. So this works for every c value when n is odd. So remember, we can take the cube root of anything. And it's valid for c greater than 0 when n is even. We can only take the square root of a positive number. Otherwise, we're dealing with imaginary stuff. So those are just some basic properties of limits that we will continue to use as we go further in these notes. So on this slide, just some more properties of limits. We've got b and c that are real numbers. We've got n as a positive integer, and f and g are functions with limits. So the limit of f of x as x approaches c is L. The limit of g of x as x approaches c is k. So we got different limits for those two different functions. So these properties are true. Number one, scalar multiple. So if I'm multiplying the function f by b, I can take the limit of f of x and multiply that guy by b. So scalar multiplication, just multiplying that limit by a scalar. Number two, sum or difference. If I want the limit of f of x plus or minus g of x as x approaches c, I can just add or subtract whichever one I want of the limits of f and g. So if I'm doing f of x plus g of x, I'm going to do L plus k. If I'm doing f of x minus g of x, I'm going to do L minus k. Number three, product. If I'm multiplying f and g, I can just take the product of their limits. Number four, if I'm dividing f and g, I can take the quotient of their limits as long as k doesn't equal 0. And the power property says if I'm taking f of x raised to an nth degree, where n, remember, is a positive integer, then I can just raise the limit to that nth power and get the new limit. So it'll be helpful probably to see those, so I'll try to keep those on the screen as we do these examples. Part A says the limit of 1/4 as x approaches 3. So this is an example of a constant function. So this limit is just 1/4. Remember, 1/4 is just a horizontal line, so no matter what the target x value is that I'm approaching, my y value is still 1/4. Part B says the limit of x to the third as x approaches 3. So for this guy, I can just use direct substitution. So I can plug in that 3, and my answer will be 3 to the third, which is 27. Part C says the limit of cosine x over x as x approaches pi. Again, I can do direct substitution on this guy. I can just do the quotient of those limits. So if I plug in pi, really we're doing the limit, hold on. So technically, I'm doing the limit of cosine x, not the, as x approaches pi, divided by the limit of x as x approaches pi. Now we don't have to show this work every time, but it's just giving you an idea of how we're using the quotient property. So if I'm looking at cosine x and x is approaching pi, well, nothing crazy is happening at pi, so that's just cosine of pi divided by pi. If you remember from your unit circle days, the cosine of pi is a -1, as pi is just pi. So we'll just leave our limit as -1 over pi. We don't care about the decimal necessarily, so we'll just leave it in the exact form. 3 more examples here. Part D, the limit of the square root of x as x approaches 12. So that's just the square root of 12. Remember, we can simplify that. We don't really want the decimal, but we want to leave it exact. So 12 is 4 times 3. Square root of 4 is 2, so that's really 2 root 3 is our limit there. Part E, the limit of x times tangent x as x approaches pi. So in this example, we're actually going to use 2 properties at the same time. Actually, we're just going to use the product property. So that's really saying the limit of x as x approaches pi times the limit of tangent of x as x also approaches pi. So the limit of x as x approaches pi, that's just pi. The limit of the tangent of x as x approaches pi. So remember, tangent is sine over cosine. So at pi, sine is 0, cosine is 1. So tangent is 0. 0 times pi is just 0. And in this last one, we're going to use the difference property and the power property. So it's the limit of 1 minus x squared as x approaches 3. So we're going to rewrite this one as the limit of 1 as x approaches 3 minus the limit of x as x approaches 3. And then we're going to square that answer. So the limit of 1 as x approaches 3, well, that's just going to stay a 1. The limit of x as x approaches 3, well, that's going to be a 3. So 1 minus 3 squared. 1 minus 3 is -2. -2 squared is 4. So our limit is 4. Last 2 kind of properties of limits here. If p is a polynomial function and c is a real number, then the limit of p of x as x approaches c, as long as there's nothing crazy going on at c, I can just evaluate that function at that target and I'll get my limit. Number 2 is just saying if I have a rational function, I can evaluate the numerator and denominator and get the limit of that rational function. So example 1 here says the limit of x squared minus 3x plus 7 as x approaches 3. Well, that's a polynomial function. Nothing crazy is happening at 3, so I can just say, well, that's 3 squared minus 3 times 3 plus 7. 3 squared is 9. 3 times 3 is also 9. 9 minus 9 is 0. Plus 7 is 7. So the limit of that function evaluated at 3 is just 7. Part B, we get to try out the number 2, the rational function rule. So the limit of x squared minus 3x plus 7 over x as x approaches 3. If I plug in a 3, this function's not undefined, so that's fine. So I'm just going to evaluate it at 3 everywhere. 3 squared minus 3 times 3 plus 7 on my numerator, divided by 3 in my denominator. Well, we already know that the numerator is 7 from part A. 7 divided by 3, we'll just leave it as 7/3. And part C, the limit of x plus 3 over x squared plus 3x as x approaches 3. If I plug in a 3 to that denominator, I get 3 squared plus 3 times 3. That's fine. So 3 plus 3 over 3 squared plus 3 times 3. So I get 6 divided by 9 plus 9 is 18. 6 divided by 18, we can simplify that to be 1/3. And then lastly, just a technology tip. When evaluating limits, we can do that numerically, looking at a table, graphically, or algebraically. Today we're doing a lot of algebra stuff. A lot of times you can use a graph to confirm what you found numerically from a table, or zooming in on the particular spot or the target x value, or using the trace feature in your calculator.